Hello, everybody. Today we're going to talk about enabling robust JBOD design via sound pressure level design targets. We have two speakers today. Myself, Madhavan Ravi. I'm a hardware engineer at Facebook. And with me today, I have Jun Shen, who's a thermal engineer at Facebook. Let's talk about the trends in the hard drive industry when it comes to capacity per HDD before we get into any details in this presentation. Here's a funny meme just to show the picture of what's happening in the past 20 years. We have gone from roughly 20 gigabytes per HDD to 14 and even 16 terabytes per HDD today. But the sad fact is we are running out of space on such a dense HDD when we didn't have such a problem a while ago. The fact of the matter is that for the next 3 to 5 years, this trend is not slowing down. Everybody probably has heard about energy-assisted recording in HDDs by this time, and I've linked in two sources from the major hard drive vendors, quoting that we will be able to see up to 50 terabytes per HDD in the next 3 to 5 years. And to quote a specific year, it's in the 2025 to 2026 range as per these two sources. If we were to see such high capacities for HDD, as a JBOD designer who wishes to reduce cost and TCO, or total cost of ownership, it's very, very useful for us to take in such dense HDDs. But this also means that the high density is achieved by higher tracks per inch or track density or per platter, and that automatically means higher vibration susceptibility per HDD for any external vibrations, and this automatically leads to performance degradation seen on the HDD when there are vibration sources. How would we like to define this problem? We would not like to have a single number for op shock, op vibe, to say this is what we have to meet in a system. That's how we have designed chassis. That's how we have gone about this problem so far. But we would like to have a deeper look at the sources of vibration, structural or acoustic, which my friend June will talk about in the next slide. But we'd also like to break it down as to various frequency components that are present in the vibration source. What is bad for HDD model? What is bad for, in general, any HDD looking 3 to 4 generations out? If we know all of that, can we build a reliable and robust JBOD that can tackle any of these problems? In general, a JBOD designer like us would design a JBOD, accept 2 to 3 HDD generations without doing anything or any changes on the JBOD. That enables us to release and accept HDDs as they come in the industry and not go through the churn of designing a full chassis every time. Listed here is also a previous OCP session where we outlined the design churn that we had to go through Bryce Canyon when we ran into an issue on supporting the HDD performance that we had to guarantee on the system, but we were failing at it because we did not know the criteria that we had to meet on the HDD when it came to vibrations. So in the end, we would like to get out of this thought experiment a transparent test criteria and a standard test methodology by which we can quantify vibrations at the HDD and vibration susceptibility that an HDD will be able to tolerate.
All right, thank you, Madhavan. There are two types of vibration in our JBOD, acoustic and structural vibration. The picture on the screen shows two types of vibrations in our Bryce Canyon. Acoustic vibration comes from the system fans and travels towards the front of the chassis, as shown by the red arrows in this picture, and attacks on a drive. And structural vibration comes from two sources, system fans and also active drives within the chassis. The unbalanced weight of the fan creates the structural vibration source, and which gets transmitted through the chassis and acts on a torque drive, as shown here by the straight yellow arrow in this picture. The active drives will also create another source of structural vibration, which will transmit through the chassis and acts on a cartridge drive, as shown here by the banded yellow arrow in the picture. Well, how do we quantify them? We built special purpose circuits for the measurements. For structural vibration, we used accelerometers mounted inside a dummy drive to mimic the actual property of the actual drive. The data connected is highly dependent on the drive characteristics and is specific to a drive model, cannot be easily generalized to other capacity or other type of drives. For acoustic vibration, we use high precision miniature microphone mounted inside of a dummy drive to measure the sound pressure levels, SPL, at a specific HDD slot. Aeroacoustics in the chassis is a system characteristics. It does not change with different drive models or drive capacity. It only depends on the chassis design and system fans. Both vibrations are very important to HDD I/O performance. Acoustic vibration typically is more critical in the broadband range with 4 kHz and above. Structural vibration is more critical at the system base frequency or natural frequency, and its lower order harmonics, which is typically between 200 to 1 kHz. The focus of this talk will be on acoustic vibration because it's a system characteristic independent of HDD models. From the JBOD design perspective, if we can establish a SPL guideline for future drive I/O performance compatibility, it will be very beneficial to a JBOD designer like us. Next slide, please. As the first step to understand the system acoustic vibration performance, we did a full chassis SPL measurement in Bryce Canyon. The NAS rule is, of course, the worst from the acoustic vibration perspective. Here's a comparison of the worst and the best HDD slot in the NAS rule of Bryce Canyon. As a plot suggests, on the lower frequency range, like under 4 kHz, the peaks of the best and the worst HDD slot in the NAS rule follow each other pretty well. However, on the broadband frequency range, there's a slight shift, but the overall trend still correlates with each other fairly closely. The delta between the best and the worst in the NAS rule of Bryce Canyon is about 3 dB on average. The next plot shows the SPL distribution across the HDD slots from the chassis front to back. There is a 20 dB delta from the front to back in the broadband frequency range. On average, the SPL improvement when we are moving towards the front wall is about 15 dB. Next slide, please. So what I just shared in the last slide was the current Bryce Canyon chassis acoustic performance. Very naturally, the next question we have is, how can we improve from here? Among many system options we have investigated, I want to share 2 design options and their impact in terms of SPL improvement. The first is the custom fan design effort with the focus of reducing the acoustics at the source. We would like to optimize the system fan design parameters such as blade shape, the number of blades, to reduce acoustic noise and maintain the same PQ, airflow, and pressure performance. As example, in one design iteration, the plot here on the screen shows the custom fan improved the broadband noise as much as 6 dB when compared to the existing model. And on average, we see about 3 dB improvement. But there's no significant improvement in the lower frequency range. The blue is a custom fan with improved acoustics. Red curve is the existing model. Both SPL measurements were taken in the same HDD slot, which is the slot 0, the worst in Bryce Canyon. The other option I want to share is the acoustic attenuation method. We applied the acoustic attenuation foams in the open area between the system fans and the nostril of the drives. The intent is to absorb the acoustic waves as much as possible and also minimize the reflection from the chassis wall after the noise comes out of the system fan and travels upstream. As the plot here shows, this approach is very effective to reduce the broadband noise. The solution can reduce acoustic noise as much as 10 dB. On average, it reduces about 6 dB in the broadband range. In the lower frequency range, however, the attenuation is not effective. And the fact is due to, we believe, in the lower frequency range, the spikes is more dominant by the structural vibration. We developed a few other options to mitigate the structural vibration problems, but this is a different topic, and I don't want to discuss in this talk. After all is done, we have a very natural question comes up. How can the vibration improvement being translated into HDD I/O performance gain? Or in other words, how much improvement will be enough to support the higher capacity drives in the vendor's future roadmap? From our system design implementation perspective, when picking the solution for implementation, there is always trade-off. Different system option comes with different complexity, cost, reliability, serviceability. The guidance from the drive vendors will greatly help us make the right decision moving forward. Next, I'm going to hand over to my colleague Madeline to discuss what the mask means from the system design perspective.
Thank you, Jun. So as Jun hinted, we would like to bring up a concept of a mask for the sound pressure level curves that have been shown so far. I'm showing here a sound pressure level curve that Jun has already shown in the previous slides, but I'm superimposing it with a hypothetical mask. Imagine if we had a passing region, a failing region, and a region of uncertainty where we could indicate that the sound pressure level needs to be clearly within the green region for us to be completely confident on the solution that we build into the system. Whereas having it in the uncertainty region gives us a line of margin or error where our judgment might not be completely true. What can we do with such a mask? If you imagine this problem as a trilemma of cost, solution complexity, like Jun already pointed out, and solution effectiveness, if we had a mask that the HDD vendors could prescribe for a product or in general the full HDD portfolio for the next 3 to 5 years, then we could design into the system a set of solutions that we can phase in either all at a time or in pieces so that we can deploy the solution with in a cost-effective manner and also enable solution effectiveness for the HDD that we're targeting at that time and moment. This discussion is something that we would like to have with HDD vendors and JBOD designers together, but the callouts or the responsibilities are definitely split. We would like a lot of input from the HDD vendors on establishing proper criteria for acoustic spectrum susceptibility for every HDD product. And going above that, highly desired outcome would be to standardize the SPL operating region into a mask of sorts, not so that it's a compliance mask that we all need to meet, but more so of a recommendation or a recommended region of operation that a JBOD designer can design to. We understand that structural vibration and acoustic vibration interact with each other, and we cannot define one without assuming something on the other end. So we would like to post this mask as a recommended mask region or region of operation rather than a compliance mask. We would also like to bring it up to the community to enable the industry to adopt a standard test methodology so that every JBOD designer can test their systems in this single standard way to be able to accommodate any HDD from any vendor out in the market. And the JBOD designers that are currently designing JBODs or systems and don't have this data with you, please check in with your HDD vendors on capacities that you can intercept in the life of your platform, and also ask about the vibration spectrum susceptibility of those HDD capacities. We have started discussion in the OCP storage community, and there have been a couple of meetings. Meeting details can be found at the OCP storage wiki website that's linked here. There is also the same presentation in a document format that has been put out for getting proposals and feedback from HDD vendors and JBOD designers. That's also linked in here. If you are interested, please log in to these documents and submit your comments, or reach out to us directly, Jun Shen and Madhavan Ravi, to get in touch with us and give us more comments on the proposal. We would like to eventually take this as a separate subgroup under OCP storage and have more progress in the next coming months. Thank you very much for staying with us. That's all we had to share today. All right, everybody, thank you for joining this session. This is Madhavan. We also have June on the call for any Q&A. We have opened this previously in the OCP storage committee and monthly calls. So this topic is not completely new. I have not seen any questions come in so far. We did receive a bunch of comments and feedback already on the proposal document. Hope to see future participation in this topic. If you have any questions, we'll still hang around for that. All right, there's one question. This is, do you have any max vibration diagrams for Bryce Canyon? At this point, the curves that June had shown, they are the worst case acoustic vibration diagrams that are seen in 2 slots on Bryce Canyon. If you download the PDF, you would see the slot number and the row number appended to the figure in the legend area. So you should be able to pick up that one. We have not exposed all of the vibration profiles in all the slots publicly, but this is the first time we are bringing it up outside. Whatever was shared was strictly only acoustic, basically maxing out the fan at 100% RPM and 100% PWM setting and measuring the sound pressure level at the HDD slots. There was a question on what's the fan RPM that we use in Bryce Canyon.
I probably can help on this one.
Yeah.
So as Madhavan just explained, when we performed the sound pressure level measurements, the fans were set to 100% duty cycle, PWM duty cycle. So the fan RPMs were around 10,000 RPMs.
All right. We don't have any more questions, so we'll give a solid 10 minutes back to the audience. Thank you, everybody. Have a nice day.
Thank you, Madhavan. Thank you, everybody.